Alright, so we've done overall limits. Limit as x goes to c of the function equals L. As long as we're agreeing, right, we can get arbitrarily close. We're agreeing from both sides, right? So this section, we're going to take a look at one-sided limits. So this right here is saying the limit as x goes to c from the right. So you're approaching it from the right. Okay, or in this case down below from the left. Let's do this first one because this is from the left. The limit as x approaches 4 from the left. Let's do it with the picture here. As x approaches 4 from the left, right? So we're approaching 4 from the left, but let's follow it. So I'm following it from the left. Again, I'm going down. And what am I approaching? I'm getting arbitrarily close to 0, right? I will approach 0. So I can approach it from the left. Could we do this by just plugging in the 4? Yeah, we can. So 16 minus 4 squared, because it's defined. It's defined there from the left, right? Now, let's go ahead and do this next one here. As we approach 2, now this time it's going to be from the right. And let me give you a little picture of this thing. In fact, let's review a little bit of pre-calc here along the way. Let me factor out a negative, so I'd have x minus 2. And let me factor the bottom. And so when this happens, I have a hole there at x equals 2. So if I plug x being 2 in, I would have a hole at, if I plug an x value into this function, what I'm left with, I would have negative 1/4. So I have a hole right there. The rest of this function is defined except for the vertical asymptote that I have at negative 2. Right, and I showed that there from the beginning there. Right, and I could course graph the rest of this. It also has a horizontal asymptote at y equals 0. Okay, so here's what this looks like, right? So let's take a look as I approach 2 from the right. Let's do it visually. As I approach 2 from the right, if you hadn't worked it out, you wouldn't know what it's really getting arbitrarily close to, right? You'd just say, oh, it's undefined, because if I plug 2 into the original, it's undefined, right? So that's why you would want to go through that same process that we did before in factoring it, right? So let's run through it one more time so that you know, hey, if you have a hole, you better factor this thing, because you can't just throw the 2 in. So factor a 2 out, a negative out, factor the bottom. So this function behaves like, again, this is a different function. All right, the only difference between these two is now it's defined at 2. Now it doesn't have a hole, right? So I just plug it in. All right. But again, we're just doing it from the right. Right? But yeah, it sure has a limit. It approaches from the right, limit's negative 1/4. In fact, if it approaches it from the left, it's still negative 1/4, right? Doesn't matter which side I approach that one from. Let's keep going. Could we plug 1 into this? And we end up with we get 1, right? So that's approaching it 1 from the left, right? So even though there's a one-sided limit, we can still plug the 1 in, just like we did before. So I guess what happens though when we plug it in, we get like a 0 in the denominator. Well, frankly, that's not going to happen in this section, so we'll look to that in the next section. But there are special ways of handling that. So, yeah. Let's look at a graph here and let's just answer. Let's see how good you are with limits, functional value, function notation, all that stuff. Let's see if we put it all together. What is f of 0 here? F of 0 is? Good. 4. That blue point up there, right? It's not defined down there, is it? F of 0 is 4. F of 2? Undefined. Good. F2 is undefined. F of negative 2. Yeah, I got a vertical asymptote. Also undefined. F of 4. 2. Good. F of 4 is 2. All right, now let's do the limit. Let me erase these a little bit. Limit as x approaches 2 from the right. Okay, so let's approach it from the right. Am I getting arbitrarily close to something? I know it's undefined, I don't care, but am I getting arbitrarily close to something? And what am I getting close to? It's about a half. I'd say that's a half. Y value there. Right? Getting arbitrarily close to half. That's my limit there. From the left. From the left, let's approach it. Same thing, yeah, that's right. It's getting arbitrarily close to a half. So, does it have? Do they agree? First of all, do both sides agree? So does it have an overall limit? And the overall limit would be 1/2. They have to agree from both sides. So it has one-sided limits. One-sided limits are the same. So yes, we say it does have a limit. Let's say what the limit is. All right, let's go to the next one. X approaches 0 from the right. So, okay, let's go back up here. Let me erase this a little bit. As we approach 0 from the right, what would I say my limit is? Bless you. 4, right? I'm approaching a y value of 4 from the right. As I approach 0 from the right. Let's approach 0 from the left. Now, let me do that in blue. As I approach 0 from the left, go back up here. Now I'm approaching 0 from the left, and I approach 1/2. Do they agree? No. You see that big gap there? So no limit. Limit does not exist, I should say. Limit does not exist, right? Because they have to agree from both sides. All right, lastly on this K, the limit as x approaches -2. So they got to agree from both sides. I'm asking from both sides as I approach -2. Well, -2 from the right shoots me up. So I already know, yeah, it's not going to have a limit. Right? I'm not going to get arbitrarily close to anything. And then from the left, they shoot me down. This really fails. Does not exist. All right. All right, let's do some special case scenarios. Limits involving sine of theta over theta. Okay. Want to make a note of that. The limit as theta goes to 0 of sine theta over theta equals 1, and there's some alternative forms of that same thing. Okay. So let's look at this. Let's look at this first one here. If I have limit as theta goes to 0 of sine of 8 theta over 5 theta, and I'm thinking, hopefully you're thinking to yourself, well, gosh, if that 5 theta is 8 theta, I'm in business. I'm in business. I need this to be 8 theta, and then I would just say that it is 1. My answer is 1, right? Well, how could I force that to be 8 theta? Well, what I'm going to do is I'm going to give it an 8 theta. Why not? I just give it an 8 theta. There you go. Well, if I do it to the bottom, I got to do it to the top, right? So here's an 8 theta on the top for you as well. So this becomes the limit as theta goes to 0 of, let me write this part out front, 8 theta over 5 theta times, this is what I wanted, sine of 8 theta over 8 theta, right? This is, yes, I'm in business here. I like this. This part I like, right? Well, 8 theta over theta, I can cancel the thetas. And so now what I'm going to do is I'm going to say, well, I could just push that 8/5 out front, and then I have limit as theta goes to 0 of sine of 8 theta over 8 theta. And I know all of this is 1. Right? All of that is 1. By the way, that should be a theta right there. So I get 8/5 times 1. It's just 8/5. So special case. So that's how I like to think about that. Let's move on to this one. I would break this one up. Theta squared over 3 theta plus u minus theta over 3 theta plus sine theta over 3 theta. Okay, and so this becomes theta over 3 minus 1/3, right? Those cancel, 1/3 plus sine theta over 3 theta. Okay. And so I can break all these up if I want. The limit of theta goes to 0 of theta over 3. So if you notice if you plug in 0 on that, right, this will be, if I plug 0 in, I'll have 0 over 3. So I'll have 0 from that minus, well, the limit as theta goes to 0 of 1/3 is just 1/3, so I'll have a 1/3 from that. And then from here, I'm like, hey, this looks pretty good, except I have a 3 theta, right? I just want sine of theta over theta. So what I'm going to do here is I'm going to push this out front. Oops. Right, because that's the same thing. 1/3 times sine theta over theta is the same as sine theta over 3 theta, right? Because I know this is 1. So I get 0 over 3, which is 0, minus 1/3, plus 1/3 times 1. Well, gosh, this stupid thing just ends up being 0. So, all right, here's another special case. So limits involving 1 minus cosine theta over theta. So you want to remember this one as well. Limit as theta goes to 0 of 1 minus cosine theta over theta equals 0. So same rules apply here as this previous one. And let's go ahead and do it with this one. And you can also, if you want to write this, this is the other form of it, 1 minus cosine k theta over k theta, right, would be 0. So in this case, I'm looking at it, I'm like, well, gosh, the 3 theta is great up there, but I need that to be 3 theta on the bottom. If I can get the bottom to be 3 theta, I'm in business. So let's go ahead and do that. I'm going to write it as 2 times 3 theta. And then I'm going to push that 2 out front. So I'll have 1/2 times limit as theta goes to 0, 1 minus cosine 3 theta all over 3 theta. And I'm like, this is 0, right? So I have 1/2 times 0, which is again 0 in this case. Yeah, they can get kind of hairy, you know, so I'll probably take a sign out of the top of those two, and a numerator there. And then I'd have and on the bottom, I'd take a 3x squared out. And then I'd have sine squared x plus cosine squared x. Well, if you remember the Pythagorean identity, what's sine squared plus cosine squared? Yeah, 1. This is 1. So what do we have here? We have limit as x goes to 0, sine x, 1 minus cosine 3x, all over 3x squared times 1. Now look at this. I'm like, well, gosh, I remember the limit as x goes to 0, sine x over x was 1, right? The other thing I wanted to remember was this one up here, the limit as x goes to 0 of 1 minus cosine x over x was 0, or kx over kx, right? And same thing for the sine x, sine kx over kx on that. So I can manipulate this because I'm like, gosh, I can take that sine x and I can pull an x out of that 3x squared. And then I'd be in this form. Notice the denominators are x times 3x. You guys with me on this? And then I say, oh, well, that's limit x goes to 0, sine x over x times limit x goes to 0, 1 minus cosine 3x over 3x. So the first one is 1. Second one is 0. Gosh dang, this stupid thing still ends up being 0. Probably. All right, let's do one more and we'll call it good here. Limit x goes to 0. I've got 9x squared. I'm going to go ahead and take my cotangent and write that as that's a cosine over a sine. Then I'm going to take my cosecant and I'm going to write that as 1 over sine of 3x. Right? And then from here I'd probably go I want sine x keep in mind you want a sine x over an x, so I'm going to introduce that. So I'm multiplying by 1 over x on the bottom, which means I got to multiply by 1 over x on the top there. And then that sine 3x, I want this sine 3x to be over 3x. So I'm introducing a 1 over 3x to the bottom. I need to introduce a 1 over 3x to the top. And then let's see where this takes us. So I got 9x squared over x, so I got 9x cosine x, and this is all over my sine x over x. Well, I like the sine x over x part because that'll just give me the 1, right? And then over here I've got 1 over 3x, and then I've got sine 3x over 3x. Let me go ahead and multiply my numerators here, right there. So I got 9x over 3x, which gives us 3 cosine x. And then I say, oh, well, limit as x goes to 0, sine x over x. So this part's right here is 1. This part right here is 1. Right? And then 3 cosine of x. What about the numerator? Well, if I throw 0 in, there's a trig function, so I can throw 0 in. What's cosine of 0? And you got cosine of 0 is 1. So we got 3 times 1 all over 1, which is 3. And at least that's one way to approach that. Hope that helps. See you next time.